Welcome to The Explainer. You know, we hear so much noise about quantum systems revolutionizing the world, but rarely do we actually get a clear, grounded picture of what's happening right now in the labs, the manufacturing foundries, and the server rooms. My goal today is to cut through all that sci-fi hype and give you a real executive summary of the quantum landscape. We're going to look at the genuine physical bottlenecks facing classical computers, the wildly unique mechanisms that make quantum computing a viable escape route, and a massive hidden shift that's currently happening across the entire industry.
All right, here is our agenda for today. We'll hit 1. The classical computing limit. 2. Bits versus quantum qubits. 3. Breaking the memory wall. 4. Four paths to qubits. And finally, 5. The secret photonic convergence.
Okay, let's jump right into Section 1, the classical computing limit hitting the wall. So look, classical computers process binary bits sequentially, right? But as our data sets are just absolutely exploding in size, we're slamming headfirst into this structural bottleneck called the memory wall. It's wild, the sheer energy and time it takes just to move data back and forth between memory and the processor is starting to completely dominate our computation costs. It's not even about processor speed anymore, it's literally about the physics of dragging an ocean of data around.
Which brings up a really critical question for modern computing. What actually happens when our data massively outgrows our memory capacity? I mean, we're pushing classical architectures to the absolute brink with things like AI training, genomics, and financial simulations. When the data gets too huge, vital information just gets locked away, completely beyond our computational reach.
And just to put the sheer scale of this problem into perspective, 410. That is the growth rate of large language models. They are growing 410-fold every 2 years. But hardware memory capacity, that's only doubling over that exact same time frame. So yeah, we are actively hitting a physical wall where our storage literally cannot keep pace with our computational ambitions. Which brings us to Section 2, bits versus quantum qubits, the disruptor. To break out of this classical bottleneck, we need a massive paradigm shift. You see, classical bits are rigidly stuck as exactly 0 or 1, classic Boolean logic. But qubits? They play by the bizarre rules of quantum mechanics. Until you actually measure a qubit, it exists as this weighted combination, a superposition of both 0 and 1 at the exact same time. This means a quantum system can explore vast exponential solution spaces all at once. The catch, though? The readout is probabilistic. The second you measure it, bam, it instantly collapses into a definite 0 or 1. So with that probabilistic collapse, you're probably thinking, wait, how do we get useful answers and not just total random noise? Well, the secret sauce here is quantum interference. Since quantum states act like waves, quantum algorithms are brilliantly designed to actively shape the probabilities. Basically, computational paths leading to the wrong answers destructively interfere. They'd literally cancel each other out, while the path leading to the right answer reinforce each other. It actively biases the final measurement heavily toward the correct solution.
Moving right along to Section 3, breaking the memory wall, the quantum space advantage.
So how does all this crack that massive data problem we talked about earlier? It comes down to this incredible mechanism known as quantum oracle sketching. By encoding classical data into quantum superposition states, a quantum processor can evaluate an exponentially large data set without needing an exponentially massive physical footprint. While classical memory scales linearly with the data, quantum systems can interact with it using a machine of what's called a polylogarithmic physical size. In plain English, the physical machine barely has to grow at all, even as the dataset becomes astronomically large. It's a total game changer for spatial compression. And hey, this isn't just theoretical math on a whiteboard. Benchmark results on real-world datasets like IMDb movie sentiment analysis or single-cell RNA sequencing have shown a 4 to 6 orders of magnitude reduction in the required machine size. Think about that. Quantum hardware using fewer than 60 logical qubits has demonstrated massive space advantages over classical supercomputers that would require millions of floating-point operations. We are literally shrinking the physical space needed to process the world's most complex data.
Next up, Section 4, four paths to qubits, the hardware race.
Now, having the math is one thing. Physically engineering it is a whole different beast. And currently, there's no single agreed-upon way to physically build a quantum computer. Instead, we've got 4 dominant hardware modalities fiercely duking it out for supremacy: superconducting circuits, trapped ions, neutral atoms, and photonics. Each of these represents a completely different physical basis with a totally unique set of engineering trade-offs. Looking at the heavy hitters here, Superconducting, backed by IBM and Google, is the most mature, but it requires these extreme, deep space-level cryogenics to keep the qubits stable. Then you've got trapped ion systems from folks like IonQ and Quantinuum, offering incredible fidelity by floating atoms in a vacuum. Neutral atoms bring dynamic reconfigurability to the table. But take a really close look at photonic systems, led by Xanadu and PsiQuantum. They use actual particles of light, photons. That means they can largely operate at room temperature, natively integrate with existing telecom networks, and, this is huge, they can be manufactured in the exact same semiconductor foundries that make the chips for your smartphone.
But regardless of the path they choose, every single competitor faces the exact same nightmare hurdle: error correction. Physical qubits are incredibly fragile. A tiny bit of thermal noise and they lose their state. That's called decoherence. So the whole industry is struggling to group a bunch of noisy physical qubits together into one reliable logical qubit. A logical qubit acts like a perfect unit of quantum info, catching and fixing errors so the algorithm doesn't just fall apart halfway through.
Which brings us to our final section, Section 5, the secret photonic convergence, the hidden consensus. While these four camps are battling it out, it turns out they're all quietly walking down the exact same hallway. There is a massive networking imperative emerging. Because whether you're building giant cryogenic chandeliers or laser vacuum traps, you eventually hit a scaling limit. You simply cannot jam a 1,000,000-qubit quantum computer onto a single chip or inside a single fridge. The engineering barriers are physically insurmountable. So the entire industry is being forced to modularize, to build smaller, high-quality processors and link them together. But here's the catch. Once you split everything into modules, you have to wire them back together. And the only physical medium capable of transmitting these super delicate quantum states over any real distance without totally destroying them is light. This creates a massive bottleneck called Layer 2 conversion. If you're using superconducting microwaves or trapped ions, you actually have to actively translate your signals into telecom wavelength photons just to get your modules to talk to each other. Because of this, we're seeing an incredible optical consensus across the board. Eventually, everyone, no matter their underlying qubit tech, has to buy the exact same light-based optical interconnects to wire their racks together. IBM is planning to link modules via quantum communication links. IonQ is emitting photons to distribute entanglement. And Xanadu? They have already demonstrated networking 4 server racks together natively using 13 kilometers of standard optical fiber. Photonic systems obviously have a massive home field advantage here, right? They don't even have to translate their signals because their qubits are already light. And trust me, the market has certainly noticed. This foundational networking and manufacturing layer is where billions of dollars are flowing right now. Just recently, the U.S. Department of Commerce announced letters of intent for $2 billion in CHIPS Act funding targeted straight at quantum foundries like GlobalFoundries and IBM. This is massive government investment aimed directly at turbocharging the manufacturing capacity in this very optical connection infrastructure that the whole industry desperately relies on.
Which leaves us with this final kind of mind-blowing thought. While all these companies are racing to build the perfect qubit in vacuums and deep freeze refrigerators, the ultimate success of quantum computing really hinges entirely on connectivity. Will the revolutionary, world-changing quantum computers of tomorrow be wired together by the exact same telecom fiber optics running under your street right now? Honestly, the answer is increasingly looking like a resounding yes. Thanks for joining me for this explainer. Keep asking questions, keep looking past the hype, and I'll catch you in the next one.